In the last lecture, we have seen the first part of SMPC, that is switch mode power converter design, rather the concept. Now we will proceed with the other types of converters. Now we start with the what are called as the flyback converters. Now a PWM flyback DC to DC converter is necessarily a different version of buck boost converter, but it uses transformer, so it is isolated. We see that transformer provides isolation, so transformer is used over here, and this is used to avoid any electrical connection, direct electrical connection, so the grounds are different, and that is basically where you get the isolation. And this safety feature is required. In fact, it is essential in many applications. We also can have multiple outputs of the transformer. We can have multiple windings, output windings, and so it is possible with this type of converter that you can have different values, different output voltages available, that is 5 volts, minus 5 volts, and so on and so forth. Now this flyback converter is usually used when the typical requirement is from 20 watts to 200 watts, so it is some sort of a low power application. The magnetizing inductance of the transformer is used to store magnetic energy. We already know the concept of the transformer. We will be more elaborate on this, because the transformer, and that is the reason why inductor is not required over here, because the winding of the transformer serves as some kind of an inductor itself. However, large transformer core is needed for higher power levels. So as the power level increases, the core also, the size of the core also is higher. Air gap is normally used to avoid core saturation. We already know the concept of core saturation. If the core gets saturated, then the if you visualize the BH curve, in that case you may have a saturation of the flux density, that is B, and it may not provide sufficient reverse EMF to counter the input voltage, and so naturally the input current may be very, very large, which may even damage the transformer. So that is the concept of core saturation. The voltage stress of the switch is high in this case. We will see why it is, and the typical applications of flyback converters are in computers and TV sets and other electronic equipment. Now since the component that is used is different here, that is a transformer, we will concentrate more on this. So in addition, the transformer allows converters to achieve much higher or lower values of DC voltage transfer functions than their transformerless counterparts. Since operating frequency of PWM converters is much more higher, that is in tens of kilohertz, even reaching up to 1 megahertz in many cases, the transformer inductors and capacitors required are very small as compared to the line frequency applications. Transformer performs different functions in the flyback converter. It provides isolation, DC isolation, that is, it stores the magnetic energy, it changes the voltage levels, and as we have already seen that you can either have positive or negative voltages both. Additional secondary transformer windings and rectifiers may be added to provide more than one output of any polarity. So a small introduction to the model of the transformer for this application. So it consists of an ideal non-inverting transformer and a magnetizing inductance Lm. So as you can see over here very clearly that it behaves exactly like a transformer, which we already know. It is a transformer, but at higher frequency. So this model reflects the ability of the transformer to store magnetic energy in this particular Lm and to transform the AC current and the voltage levels. So we know the functioning of transformer. This is the topology for the flyback inverting converter. So as you can see, you already have the DC here, and pulse rate according to what we have already seen. This transistor or the switch in more generic sense will switch on and off according to the input at the base, and correspondingly I will have some kind of a pulse kind of a behavior, pulsating kind of a behavior, and that is actually coupled to the output stage. And here this, if you look at this part, it is behaving just like, so this part, it is behaving just like the inverting converter topology or the buck boost converter topology that we have already seen. Again, we can see here that I am in a position to get the negative voltages out of this. This is the flyback non-inverting converter. So this is just like your buck converter. So this part, if you look carefully, it looks very much like a buck converter. In fact, it's very simple to visualize this, because this capacitor will be acting only as a filter capacitor. So whatever are the ripples over here will be dampened by or bypassed. The AC content will be bypassed by this capacitor. This is the flyback converter regulator. Now again, we'll be interested in having the regulation. So the feedback and the regulation part, it is exactly like the one which we have seen earlier in case of the other converters. So necessarily this gives you isolation. At the same time, you can see the grounds are different here, so this signifies the isolation. And we have the feedback. Next type is called as a forward converter. So it is one of the most widely used converters. It is single-ended isolated converter and can be derived from the buck converter. Belongs to the family of buck derived converters. A core reset circuit is required in this converter. The transformer is not required to store magnetic energy. Again, in this case, the switch must handle high voltage stress. Forward converter is suitable for low and medium power applications, generally ranging from 30 to 500 watts. So for different applications, we have different topologies which are suitable. It is used in either single output or multi output power supplies. So this is the topology for that. Here, one additional thing that you see over here is there is one more diode over here and this particular mechanism. So this is actually the core reset mechanism. Okay, this is the forward converter regulator. Okay, so when we talk about regulation, naturally we must have the feedback available with us. Then another type of converter is called as a push-pull converter. As you can see, there are two switches involved and these are complementary, or they behave in a complementary manner, that when this switch is on, this is off, and so on and so forth. So naturally you have a positive going pulse and a negative going pulse. So this is coupled at the output again with the help of the transformer, and you can see this is simply a full wave rectifier with center tap. It is the same principle, it is exactly the same. Okay, and then at the output you have the LC filter. Instead of only the capacitor filter, we have the LC filter over here. So this is the only difference. Again, whenever you want to have some kind of a regulation, you need the feedback mechanism, and this feedback, again using the pulse width modulation, we can change. As you can see, this is a complementary drive. So as you can see very clearly over here, this is a bubbled output over here. It means, it signifies that these two transistors are working in a complementary fashion. Components in SMPC design. Now we go on to study the design part. So switching device, that is, can be either a bipolar junction transistor, high power, of course high frequency, a MOSFET. Most of the times no MOSFET is preferred, or even the insulated gate bipolar junction transistor, which is somewhat cross between a BJT and the MOSFET. Then we have the diode, high power switching. So the specifications are different here in this case as compared to the linear power supply devices. So I am here stressing more on the specifications part. So what type of components are required in the SMPC design? That is what we are discussing. Capacitor. Now this capacitor is a special type of a capacitor suited for high frequency applications. Remember, our switching frequency is no longer a low frequency like power line frequency. It is to the extent of tens of kilohertz. Inductor, again designed for high frequency. And then we have the PWM control loop. Now this control loop actually involves what is called as a compensator. In fact, these are all integrators, special type of integrators. We will see they are classified into type 2 and type 3 compensators. Compensation or compensators is a word which is used in instrumentation. So we electronic engineers call it as either the integrator or the low pass filter, whereas instrumentation people will call it as a compensator. Ideal versus practical BJT. Now when we talk about switching, this is very important, because the transistor is used as a, the BJT is used as a switch. In that case, ideally speaking, the transistor should switch on and off like this. Okay, so this is the time axis, and whenever I have the base voltage, it should exactly follow this, but practically it doesn't exhibit this behavior. This is what is the actual behavior. Okay, so when the transistor is off, IC is not exactly equal to 0, it is equal to the ICBO, okay, which is the leakage current, right? Remember that bipolar junction transistor, when the transistor is off, the collector base junction is reverse biased. At that time some reverse current will also flow, but it is very, very small. It is due to the minority current carriers, and of course this is temperature sensitive. Now whenever the base voltage goes high, immediately the transistor does not turn on. It takes some time and you have a behavior of this fashion. So naturally we have to take care of these things also, and as you know, these parameters are important when we talk about fast application, that is a fast switching of the device. So delay time, rise time, storage time and fall time, TD, TR, TS and TF are very, very important over here. It is signified over here. So whenever it requires to go from 10% to 90% or 90% to 10%, we know that they are called as the rise time and the fall times respectively, and there is additional time called as the delay time and the storage time. So these times are also very, very important. These time intervals actually decide what will be the behavior of the transistor at higher frequencies. So as you can see here, that these characteristics or these parameters have to be considered for the typical application. The maximum switching frequency versus upper cutoff frequency. We know that the transition frequency FT or FC, whatever it is called as, we know that we have a certain transition frequency FT where actually the HFE also becomes equal to 1, where the device does not remain or cannot work really as an amplifier. Of course we are working here the transistor as a switch, but in that case also there is an upper frequency at which it really after which it is not possible for the transistor to keep up with the input signal. So for example here 2N3904, which is a high frequency transistor, you have TD as 35 nanoseconds, TR as 35 nanoseconds, TS as 200 nanoseconds, TF as 50 nanoseconds, and the upper cutoff frequency is given here as 0.35 divided by TR, that is the rise time. So for a transistor to pass a rectangular waveform with minimal distortion, its cutoff frequency must be at least 100 times. This is again a design rule. Okay, so while selecting the transistor you have to take care of these things. Frequency of the input waveform, so FSW, which is less than or equal to 0.35 divided by 100 into TR, or the switching frequency maximum should be 100 kilohertz in this case. So corresponding to the switching frequency that you are selecting, you are supposed to select the transistor based on these criteria. AC volt switching, current to voltage overlap losses are also there. Leakage inductance in inductor or transformer causes a very rapid voltage collector voltage fall time, because for a short time at t equal to 0, for a fast current step an inductor behaves as an infinite impedance. So this is a very important aspect. Since current cannot change instantaneously through the inductor, it rises slowly through it. Therefore there is a very small overlap of falling voltage and rising current at the turn on. So at the specific point, see the transistor current is not completely removed because of the inductor in the collector circuit, and that is the reason why the collector, while switching off, the transistor still will be having a significant amount of current, the collector current, and the rise in the voltage across the transistor will also be significant. So this is where the overlap occurs, which we had earlier assumed in case of an ideal transistor, that the current and voltages both cannot be maximum at the same time because it behaves as a switch. But practically this is going to be a problem which you have to take care of. So this overlap is significant at turn off most of the times. So selection parameters for BJT and MOSFET. So in case of BJT we have to just like what we have used the selection parameters in case of the LPS, which we have seen in the class earlier. BVCO, that is the breakdown voltage, that is the maximum voltage across collector and emitter of the transistor. BJT, when the base is open. Similarly we have VDS max in case of the MOSFET. So this has to be taken sufficiently large, as we know that we use factor of safety for that. So we have to find out what is the VCE max, and correspondingly we have to select the device so that it is capable of withstanding this particular maximum voltage. IC max in case of BJT, in case of MOSFET it is the source drain current. In case of BJT we have to find out what is the IC peak. Remember that the continuous current and peak currents are different. PD max in both the cases. TR, as we have already seen, the rise time for both the devices. Okay, that will be less than or equal to 0.35 divided by 100 times the switching frequency. In case of MOSFET, RDS will be also an important thing, because it is a channel resistance, and the maximum current when the device is on, the maximum current multiplied by the square of the maximum current multiplied by this RDS is the power dissipation. Then in case of MOSFET, you have the output capacitance, the total gate charge, and both the cases we have the safe operating area. Now advantage, both the cases, so in both the cases you have the safe operating area consideration. We have already seen the concept of safe operating area. Advantage in case of MOSFET is that as temperature increases, in case of BJT, you know, it may lead to thermal runaway, so heat sink requirement is very severe, whereas in case of MOSFET, actually the output resistance increases rather with the increase in temperature, and so the drain current actually drops down a little bit. That is one advantage of the MOSFET. So it is of course heat sink is required so as to maintain the junction temperature to the expected level, but MOSFET is having an advantage over there. Then the diode. A very interesting thing about the diode is that this is not the normal conventional rectifier diode that we are using. It is called as a fast rectifier diode. As we have already seen in one of the classes that when a reverse bias diode is rather a forward bias diode is suddenly reverse biased, what is going to happen? Okay, so you have a forward bias diode here, and if you see that the current flowing through the diode, we know that the diode will be on, then it is forward biased, full load current will flow through it, and as soon as it is switched off, the current flowing through the diode does not abruptly become equal to zero, but for this particular time the current will still flow. Please remember that it is flowing in the reverse, sort of a reverse direction, so it takes some time for the current to become zero in the diode, and that is the reverse recovery time. Okay, TRR, we have already discussed this TRR many times in the class. So we have to take care that the TRR is less than or equal to 1/10 of that of T, where this T is the period of the switching frequency. So selecting the fast rectifier diode is also a very important task in SMPC design. Then these are the various options available to you. So as you can see here that we normally use the Schottky diode or the ultra fast diode or the fast recovery diode. Okay, and just for comparison purpose, I have given here the standard recovery, that is a rectifier diode which you normally have used so far, that is 1N4001 sort of series or 1N540 series. In that case you can see the reverse recovery time is 1 microseconds, whereas for these special devices you have less than 10 nanoseconds. So it is in nanoseconds. Okay, so this is basically this can be used only for the line rectification, whereas these types of other diodes will be used in our SMPC designs. Capacitor also is a very important component over here, and this is not the capacitor that we already have used or we normally use in the linear power supply, because at higher frequencies the model of the capacitor is not purely capacitive like this, but it has got some equivalent series resistance and equivalent series inductance also associated with this. ESR is because of the dielectric, probably maybe like that, or the ohmic resistances, that is the lead resistance, again this is the lead inductance. So we have it is actually looking like a series RLC circuit. Okay, so if you remember, I have actually shown you that if for up to a particular frequency it will behave as a capacitor, but then if you exceed that particular frequency, the inductive component will become more dominant, and your capacitor will start behaving like an inductor after the resonant frequency. So this is a very interesting issue, and your capacitor, if not selected properly, will behave as an inductor. Of course, it depends on the frequency of switching. Alright, so these are the various different types of capacitors that you can use over here. Just for comparison, I have given you the electrolytic also. So ESR is very poor in case of electrolytic, so these are most of the times used, but there are special designs for these types of capacitors, whereas ceramic and film times are fairly good for these applications. The advantages of ceramic capacitors compared to other capacitor options: ceramic capacitors offer extremely low levels of ESR and ESL, and they have a predictable performance. Characteristics related to temperature, voltage and frequency just make them the preferred choice, especially in case where you require high reliability and given the high frequency application in SMPS designs. In addition, unlike film and electrolytic options, ceramic capacitors offer a maintenance-free, environmental friendly choice. So this is again a very important issue, especially from the environmental friendly design kinds of approaches. Transformers used in SMPS, used in switch mode power supply circuits are significantly different from power transformers that are used in our usual step down configurations. These are the important differences. Input and output voltages and currents of SMPS transformer are mostly non-sinusoidal. As I said, if you go back and see the push-pull type of a rectifier, push-pull type of a converter, in that case you are going to have mostly a rectangular type of signal over there, whereas the transformer connected to utility AC are almost always sinusoidal. So this is one major difference. Currents and voltages of SMPS transformer are of very high frequency, whereas that for the line voltage applications they are low frequencies. SMPS transformer generally handle much smaller power than the utility transformer. So this is one more difference. The core, basically because of high frequency operation, the core is different. In case of line frequency transformers, you have the iron core, whereas in case of high frequency, most of the times you have the hard magnetic materials like ferrites, where the low frequency use something like iron, silicon, steel, etc. Ferrites have very high ohmic resistance, and the area enclosed under the hysteresis loop, if you imagine the BH curve, is significantly lower. So you have a thinner kind of hysteresis loop. As a result, even at very high frequency operations, the hysteresis and eddy current losses are low, and that is one of the biggest advantage of switching power supplies, because the transformer losses are very low. Ferrites have low magnetic permeability. Typically, the value is about 100, and low saturating value of flux density around 0.4 Tesla, which are considerably less than that of the silicon steel. Ferrites are also brittle and fragile. So there are some challenges, some advantages and limitations. This is an example of the buck converter design. I'm not going to run through all the steps. I'm just going to flash it so that you can verify the designs. The designs are again given step by step as our usual method. So this is for the buck converter design, which operating in the continuous current mode. We have already seen the two modes. So input is 28 volts plus or minus 4 volts. Output required is 12 volts. Minimum current is 1 ampere. Maximum current is 10 amperes. Switching frequency is 100 kilohertz, and the maximum ripple that is allowable is 120 millivolts. So you can use these equations to design the buck converter. Okay, so it actually has more than about 20 steps, and it gives the selection of the capacitor and the inductor, the device parameters also, like MOSFET and the diode. So you can just freeze the video and have a look at these designs. Alright, so about 21 steps culminating with the calculation of the efficiency, and you can see that the efficiency is pretty high, about 90, in excess of 90%, and that is one of the biggest advantage of the switch mode power converters. Remember, we are still with switch mode power converters. We have not yet talked anything about the switch mode power supply. In case of DCM, you have a slightly different approach for the design. So these are the design steps for DCM. You can just go through the design. I have given the complete design in these slides. Again, 20 steps. Here you can see again the efficiency has been calculated. This is for the boost converter design. Again, similar kind of approach, different steps though. So you can just have a look at this design also. The design steps are quite simplified and they are self-explanatory. I need not run through each and every step. Just go through the steps. And whatever devices, you can just download the data sheets and verify whether the parameters are correct or not, suitable for our application over here. So 23 steps here. This is the buck boost or the inverter design. Remember, the output in this case is a negative voltage, and you'll see that most of the times the maximum current is 10 amperes. So it is a de facto standard that you should not use linear power supply for large load current applications. Most of the times we limit it up to 2 amperes linear power supply, whereas whenever in excess of 2 amperes we generally prefer the switch mode power converters. Again, similar kinds of steps. Then this is the design example for flyback converter. Again, continuous current mode. We should see a markedly change here in the marked change in the efficiency here, slightly lower efficiency because we are using transformer here. So this is for forward converter. So it is all given in form of steps, very systematically given. So it should not be a big problem if you do this exercise on your own. This is for the push-pull converter. Yes. Now the other part which was remaining was the control loop design itself. As you can see here that we have the sampling, and then we have this error amplifier here in this case. Now the compensator, as I said, or integrator and error amplifier, both most of the times they are implemented with the same circuit. Okay, so we'll see how this control loop now is designed. So the basic op-amp configuration and its isolated counterpart are something like this. So whenever we require an isolation, you have an optical isolator over here, or an opto isolator, and this can be given. Please remember that in case of the isolated power converters, we have to have different grounds. All right. So this is actually the output side, and this is the input side, other side of the transformer. This is an error amplifier, which is an integral single lead controller, or type 2 controller as it is commonly called as. The task of this lead controller is to reduce the phase lag and therefore achieve a high gain crossover frequency while maintaining a specified phase. Now this is concerned with the stability of the system. So whenever we are talking about a feedback and that sort of, so it's a control system, so the stability of that control system is very important. This type of controller provides basically some kind of a it maintains high gain. I mean, it gives you high gain at the same time maintaining the specified phase margin, because if you remember from the control theory that if there is a sudden change at the high gain and you have a particular value of phase, then in that case it may lead to instability, and that basically is to be avoided at all costs. So whenever you want to make the system stable, you have to have some kind of phase margin. So this is how it looks like. So for a particular band of frequencies, up to this particular band of frequencies, you must have a particular phase margin, okay, over there. So this ensures that we have a stable system. So these are the actual outputs, simulated outputs for the type 2 controller. As you can see, in this particular region you have a sufficient phase margin. This is the design example. You can just go through this, how to get the phase margin, and these are the outputs. So you can see very clearly this is an integrator, just as an integrator, that's all. So this is type 3 error amplifier, or also called as a double lead controller. Alright, this is your feedback, and you have some additional network over here. This actually gives you a better phase margin, as you can see here in this case. Then we have what is called as the requirement of a startup circuit. Now what is a startup circuit? Your PWM controller does not have any power supply. Most of the times we require 12 volts DC for this, and we don't have DC to begin with. We have a very high voltage DC over there. But then who is going to provide, for at least for starting up, who is going to provide? Because unless and until PWM starts working, it will not be able to switch the transistors, and this will not be able to induce any voltage in the secondary, and no DC available before that. So who is going to start the PWM? That is the job of the startup circuit. This is a simple startup circuit. As you can see over here, that it is derived. Once you have the startup circuit, the basic job of the startup circuit is to give a supply of 12 volts to actually start the PWM controller in the first place. And when it starts, then this can become dormant, and then you can generate from this winding, you can generate the DC supply which is required for the PWM controller and the opto isolator or the optocoupler part. So this is the simulation. A very high voltage DC, maybe up to 400 volts, and you can see here that it rises up very fast, and because of this Zener diode I am able to get 12 volts over here. And once your auxiliary winding starts giving you voltage, this diode makes sure that it is going to cut off this part from this part, that is this capacitor is isolated in that case, and then the normal working can start. Then we have a couple of ICs which do the job of, as I said in one of the demos, that we had a PWM controller, LM3524 or LM1524 or SG3524 depending on the company which has manufactured it. This is a very favorite kind of, mostly preferred kind of PWM controller IC which you can use. You can download the data sheet and study it. This is the internal block diagram. As I said, things are very easy for you to understand here. That we have an oscillator where you can generate the ramp signal for the comparison purpose. We have an error amplifier. Okay, so output is given to the comparator, and then we have the switching of the transistor. These are the drivers which we can use for driving the output transistors, which are the switches actually. This is a typical configuration given in the application notes. These are the design equations specifically for this IC, so you can design this very easily. This is the configuration for buck regulator. This is the configuration for buck boost regulator, and this is for the boost regulator. So you can use the design equations to find out the values of different components. Very few external components are required in this case. Okay, fine, that's it. So we complete the part 2 of SMPS design. The demo for these circuits that we have seen in this part will follow shortly.